All right, guys. So what we're going to do is start moving into the last thing here, and that is electrochemistry. So let's talk about doing some electrochemistry. Oops, I need to get my participants and get you guys as my ruler on the side. So out of curiosity, can you guys see the participant list as I move it over? Or do you just see my OneNote writing?
Just OneNote, but we can pull up a participants list ourselves.
Okay. I was wondering just exactly what you guys see. All right, so electrochemistry. It's essentially part and parcel to the Gibbs free energy, because as we sort of showed last time, delta G equals negative NFE. And I did this with that demo last time, not really explaining it, so I'm going to explain a little bit more here. Keep in mind, if we can have a delta G naught, we can have a negative NFE naught as well. So we can do things at standard conditions. And just to remind ourselves again, delta G is the Gibbs free energy. And now N is going to be the number of electrons transferred. F is going to be Faraday's constant. So you guys might have heard of a Faraday cage. That comes from Mr. Faraday himself, who figured out a lot of stuff about electricity. That value is 96486 coulombs per moles of electrons, or the number of them. And finally, E is voltage, which is, given the symbol V, probably intuitive there. This is also called an electromotive force. So it's the force from the movement of those electrons. It's a driving force. It is essentially being out of equilibrium and trying to go back to. And I just want to remind us that, remember, delta G is negative. That means E will be positive. This will be spontaneous. So we already had our frame of reference for delta G, but it's kind of counterintuitive to think of negative voltages being spontaneous, so we put a negative sign to take care of that. I also want to remind us as we go into this that delta G and delta H are extensive. And that means it depends on the amount. Depends on how much you have. You have twice the gasoline, you got twice the explosion. In contrast, E, or voltage, is intensive. That means it is independent on how much. And our example of that was AAA versus the D cell. Both are 1.5 volts. It just means the D cell is going to last longer because you have more material, but both of them give you the same voltage because they both have the same materials in them, and it's all about the materials, not how much. That NF factor is what converts delta G to E, and it's just basically a scaling factor. Okay, so now that we have those pieces there. I want to go back to an experiment that is a classic one. This will be very similar to one that you may have seen in Chem 110. So a classic example. This is where you take some solid zinc. You drop it into some copper 2 nitrate. Now at this point, you might recognize what type of reaction this is. Contreras, you joined us. What kind of reaction is this? Moving on, Mr. Snow. Oh wait, you weren't one of mine from that, so you may not remember. But Chef should remember what type this is. Anybody?
Like a single replacement?
It absolutely looks like, and it is a single replacement. So on the other side, what that means is that the zinc is now swimming and the copper is now solid. Move that over. Try that again. And the copper is now the solid. Okay, so the single replacement, okay? Now, if we were to write the actual net ionic equation, so if we go down to the net ionic, you guys remember those guys? Essentially, this would turn into solid zinc plus a copper 2 plus floating around. They'll switch places, and that zinc would now be floating around, and the copper would be solid. So for the people who've been with me all the way since Chem 110, you might recall this with the silver and the copper, when we dropped that copper rod into the silver nitrate, and that rod became fuzzy. That was our single replacement. But really what was happening here is electrochemistry, what we'll refer to very quickly as a redox reaction. So what happens here? Zinc, it's fuzzy with deposited copper. So if you were to do this, you would see that that chunk of zinc would slowly start growing little hair-like things on it, and it would look like it needed a haircut pretty soon. And again, for those of you who remember that copper rod with the silver nitrate, it might pull up some memories there. Now, what's really happening here? When this happens, okay, you got these coppers floating around, they go over, they accidentally bump into the zinc, a reaction occurs, a single replacement occurs. Now, we used to think of this in terms of like, well, the zinc is going to take the nitrates and go swimming, and we're going to make the copper sort of just like sit out and deposit out, precipitate out. But here's what's actually happening. This is what we didn't tell you back in the day, that the zinc gives its electrons to the copper. This is what's happening. The zinc, if you look at it, goes from a zinc with no charge. Now, we don't normally do this, but I'm going to do it for illustrative purposes. It's got no charge there. It gave up its 2 electrons to become a zinc 2 plus. The copper said, oh, I'm going to go from a 2 plus down to a 0. I must have gained those electrons. This transference is what we call a redox reaction. So when we look at this, this is called an oxidation reduction reaction. commonly called redox for the obvious things here. We say it's an oxidation reduction reaction. We call it a redox because I guess oxy-red is weird. So people talk about redox reactions, and really it's about a transference of electrons. Now, there are a couple of different acronyms that you can use to remember some of these. I like this one. Oil rig. There's also Leo the Lion says GER. Too many words for me. What does this mean? Oxidation is loss of electrons. The reduction is the gain of electrons. And so you can see the acronym here, oil rig. So as we start looking at these reactions, what we want to do is keep in mind who is losing electrons, who's being oxidized, and then who is gaining the electrons, who is being reduced. And we'll be doing a lot of these, so don't fret. Now, I want to point out in this reaction right here, where you just take a chunk of zinc and you toss it into the copper nitrate, copper 2 nitrate, it gets fuzzy. Big deal. Transfers electrons, big deal. What does it do for us? Remember, we are humans and we are incredibly selfish people, things, entities. What can that do for us? This is about thermodynamics. We're talking about, do you want to go? And Gibbs says, can I get anything out of you? So let me point out that since the transfer of electrons does not accomplish much, except to get it fuzzy, we have to do something to get that work out of it. We must do something to extract the energy of this transference. And here's what we do. There's a couple ways of doing these, and I'll go ahead and show you a couple of the common ways of separating these and then extracting the work. One of them is what is called an H cell. So what we're going to do is we're going to separate the two and, quote, make them go through us. Meaning we're going to make this reaction go, but we're going to make it go in such a way that this transference of electrons has to go through something that we want it to go through to essentially power it. And here's how we do it. Let's see. I thought about actually just importing a picture, but then you guys wouldn't be able to follow along. So I'm going to draw something that we call an H cell. I probably don't want to do that. Well, shoot, that's all right. It's so named because it looks like a H. Now, this H cell has a little thing here in the middle. This right here is a semi-permeable membrane. semi-permeable membrane. That means things can get through, just not very easily. All right, so what we're going to do is we're going to take this and we're going to put in some zinc. And I'll put zinc in, I don't know, red. Why not? No. I like copper being red because copper is kind of a reddish color. I'm going to put some copper on this side. Then I'm going to put some zinc on this side. They're both metals. We'll just get a little rod of them or a plate of them. We're going to stick them in a solution. Oh, so let's make a little solution here. Okay. So what we're going to do now, we've completely separated them. What we're going to do is now connect them and let them see them. We're going to do that by putting here a nice little voltage thing to say, look, you see this wire? Now you guys can see each other. You're essentially touching. Go ahead and transfer your electrons. It goes like, okay. So the zinc wants to throw its electrons over, okay? Which means we're going to have to start having a charge imbalance. That's not a good thing. Remember when we talked about balancing equations, we always talked about balancing the atoms, but the other thing that is inherently balanced too is the charge in any system. You can't have a place where you, well, I mean, we talked about it in Chem 120. If you were to go get a bucket of seawater and you were able to separate out the positives and negatives, you would find out that you have exactly the same number of positives and negatives. It cannot be any other way. It just is. So if these electrons are heading over to that copper, there must be some sort of attractiveness to that. And that attractiveness is the fact that the copper would be our positive electrode. Which means if the copper is positive, then the zinc is negative. Okay, so now here's the fun part. We said that the zinc, was becoming zinc 2 pluses. We said that the copper 2 pluses were becoming solid copper, right? If we look back up there real quick, that's what we said was going on. We said that the zinc was becoming zinc 2 pluses and that the copper 2 pluses became copper solid. So check it out. How does this work? We have electrons going from the zinc over to the copper. That means there's going to be a buildup of negative charges over there. Well, if that negative charge starts to do that, then what we have down here, say in a 1 molar copper 2 sulfate solution, is you have a bunch of copper 2 pluses. As soon as those electrons start to flow to the copper, those copper 2 pluses race up there to grab them. And of course, as they grab them, they start to deposit. So, copper 2 plus, race to grab those electrons and deposit on the copper electrode. Let me make sure that's a nice U here. Now conversely, in order for those zincs to suddenly spit off the electrons, they have to become zinc ions. Well, zinc ions can't just sit in on the solid. So what ends up happening there is that and let me see if I can do this nicely. I knew that was going to happen. Is that the zinc will now have to spit off some of itself in the form of the ions. And down here we might have, say, a 1 molar zinc sulfate solution. Okay, so we have a flow of negatives over toward the copper. Copper 2 pluses are running up, seeing those electrons, going, thank you very much. They get their charge reduced because they gained those electrons. They now become solid copper, and they start piling up on that copper electrode. The zinc, in order to do this, has to give those electrons up. Well, the only way to do that is to take them from one of itself, creating a zinc ion, which will pop off and float around into solution. You guys with me so far?
Yeah, just to clarify, this is just a wire. There's no battery or anything, right?
No. So this little V thing right up here, this could be anything. It's your this guy right here. Let me see, what color should I use? I'll just do blue. This is your iPad device using those electrons. So in the case of what I did with that dilution thing, that dilution example where I stuck the electrodes there, the energy that was generated could be read by that voltmeter. So basically that energy was flowing through the voltmeter and showing us the voltage. In this case, what you do is you'd have your electronic device, and that flow of electrons through it would actually power the device. And so that's what that V commonly stands for, some sort of power-like device. And it's either generating power or consuming the power. And for us, it's consuming the power. In physics, they like to generate it for their circuits. For us, we like to suck it up so we can listen to music.
So is it like pushing and pulling the electrons?
It's actually just watching it flow through.
Okay.
So much like, say, a paddle wheel, a water wheel uses a river to push the wheel to move the stone to grind the flour. All it does is watch the flow of the water. It's not pushing the water, it's not pulling the water, but that flow of the water moves the wheel, moves the stone. Now we have flour.
Got it.
So it's the same sort of thing. But remember, Chef, electricity is magic. So sometimes you just accept that it works. Because let me tell you, the physical thing of water pushing a wheel, that makes sense. The idea of this thing that I've never seen before suddenly making my laptop work, I have no idea. The fact that I put a stylus on this page and blue stuff comes up, magic. If it's not magic to you, you're not thinking hard enough. All right, so here we go, that the zinc dumps electrons becomes zinc 2 plus and floats off into solution. Now, the reaction on this side would look like zinc goes to become zinc 2 plus. Remember I said that we had to keep track of charge? We're going to keep track of it by saying the zinc broke apart or dumped itself off and became zinc ions and 2 electrons. It produced 2 electrons. On the other side, we had the copper gaining those 2 electrons and becoming solid copper. These are what we call the half reactions. These guys are the half reactions. Half reactions. Basically, we take what is the overall reaction of zinc and copper ions, et cetera, and break it apart. And what we've done is we've broken it apart by putting it into two separate compartments and saying, you guys can't see each other. Not until I connect that wire. As soon as you have that wire, you guys can see each other, and now transference can occur. One last thing to note about this, I said it was a semi-permeable membrane, and that means that if I have negatives going one way, here to the right, I'll have too many negatives on the right. So something has to give. Tristan, what do you think has to give?
Sorry, I wasn't paying attention. What's that?
Oh, that's fine. Then we'll go to Pat, or no, Soto. If a bunch of negatives are going to the right, then to complete the circle,
Positives must go back to the left.
what was that again, Tristan?
Positives have to travel to the left.
Actually, negatives. You have to complete the circuit. And so, yeah, this is where it gets kind of interesting. And this is where we'll set the Wayback Machine for some of you who've been with me for a while. In order for the circuit to be completed, electrons flow through the wire, but the charge, the current, is carried through the liquid solution by the ions. So for those who were with me in Chem 110, we talked about electrolytes very briefly. I said that electricity is the flow of electrons, and current is the flow of those ions in the electrolyte. Here you can see that the circuit has to be completed. If you have negatives flowing to the right, they have to continue to go back to the left to keep that balance. Otherwise, you've unbalanced the circuit, the circuit, and it will break. So what we do in this, and I should point out that real quick, that this guy right here, this zinc going to become zinc 2+, and the 2 electrons. This is the oxidation because it is losing the electrons. And this copper 2+ gaining those 2 electrons is the reduction. So when we start doing these equations, we're going to break them up into their half reactions. We're going to break them up into their oxidation reaction and their reduction reaction. And one last thing to note, since we are here, we're going to put everything in one spot, and we'll keep doing this. This zinc, the oxidation here, the oxidation is the anode. And you might remember this as A negative electrode. And the reduction is the cathode. And I do this by CPR, which means cathode positive reduction. Couple of cool acronyms to help you remember which one's the anode, which one is the cathode.
I know one too.
What?
An ox and red cat.
An ox and red cat?
Yeah.
Never heard of that. I'm gonna put it in here. Jeff says an ox and a red cat. I just learned something. Never heard that one. Wait a minute. How did you find those?
Some YouTube video.
Being such a good student. All right. Another way people do this. And it's still pretty much widely used. The H cells are becoming much more prevalent, but the old school way was this. Well, actually, there's a third way. There's a porous cup, but the salt bridge is another one too. So another way people do this is they will get two completely separate cups to house their materials. They will still put in the copper. They'll still put in the zinc. And they'll still keep these solutions here. I'll talk about why we need the solutions here in just a second. I'm just being thorough at the moment. Go ahead and put them in a watery environment. And this is where it gets kind of cool. We're still going to attach them. And don't worry, I'll give you plenty of time to write this down in a second. Attach them with a wire. But we still have to make them see each other completely, because if we can have the electrons still flowing across here, if the electrons are still going there, someone has to go back the other direction. And that's where this guy comes in. And this is called a salt bridge. Now the salt bridge is usually a jelly-like substance. Filled with ions. Maybe something, for example, you could have potassium nitrate up in here if you wanted. Let's see if I can make that look a little better. Now, this salt bridge has an advantage over the other cell. The other cell, that semi-permeable membrane, is usually some sort of sintered glass, meaning it's glass and it's got really, really tiny pores in it and allows things to go through and move through. But what if you did not want that ion, that sulfate, going back the other direction? What if that sulfate would mess things up? What if the electrolyte on one side would mess with the system on the other side? In the case that we have here, they're both sulfates on both sides. It doesn't matter. But there are cases where the solution on one side, if it does permeate across, it would mess up the other side. I mean, there's a reason why we're keeping them separate in the first place. So in this case, what you would do is you would take a salt bridge full of a different type of salt. We just need something to carry the charge. So we do a different type of salt such that if these sulfates here try to go up and through here, the potassium nitrate goes, back off, I'll take care of this. You can start backfilling me as I push out over here, but I don't want you to get all the way over. And so it's a way to even more effectively separate out these two electrodes if that's something that is needed. Does that make sense?
So the KNO3 reacts with the sulfate?
No, does not react, right? So if you have a sulfate, so I'll actually go ahead and put it in words here. Sulfate tries to move to zinc. Instead, it creeps into salt bridge. on the right. And NO3 pops out the left. Think of shoving in BBs, right? You have a sulfate trying to get in here. So let's say that sulfate is trying to come in here. Out the other side, instead of that, you're going to see some nitrates pop out to continue that charge, that current. And so, like I said, in this case, it doesn't matter because they're both sulfates on both sides. We'll see other systems where what would happen on if the counter ion, as we call it, the counter ion, if it goes across and actually sees the other side at all, it's going to start poisoning it. In this case, the sulfate would try to go through. The nitrate says, you know what, you just go ahead and keep pushing me into the other side and I'll do your job for you. You just reminded me that I do need to call this the counter ion for you. Because it's counteracting the flow of the electrons. Oh man, electrochemical cells, there's a lot in there. We'll build a ton of these guys, so just stay with me. All right, did that help you, Chef?
Yeah.
Okay. All right, so before we start building these things anymore, I just want to show you what they physically look like. Let's talk about these oxidation and reduction reactions and how we're going to build them and balance them. So first, we need to learn how to balance these reactions. Now, I'm going to go ahead with 9 steps. The first 6 will be the same for both. The last ones will be used in special circumstances. So, first we learn how to balance these reactions in acid, then in base. So I'm going to go ahead now in the acid. So most of these redox reactions will use acidic conditions. I mean, if you think about it, your car battery is full of sulfuric acid. It's a great electrolyte. So a lot of things we want to do tend to have acids as their electrolytes. And so what we want to do is learn how to balance these in an acid, and we'll continue this on into a base situation because there are actually commercial examples of where a base has been used. So let's do this. The first thing you want to do is you want to split the reaction into the 2 half reactions. Split the reaction into the 2 half reactions. Okay, so those are your oxidation and reduction reactions. Okay, so I know I'm going to come back so you can finish writing it, but what I'm talking about here is when we took this overall reaction right here, getting rid of the spectator ions, and we ended up breaking it apart into its 2 half reactions that we see here. That's what we want to do. We want to take the overall and split it up. And we'll do this to each of the halves, okay? So to balance each of the halves, number 2, balance all atoms who are not oxygen or hydrogen. Balance all atoms who are not oxygen or hydrogen. Number 3. Add H2O. Balance the oxygens. Number 4. Add H plus to balance the H's. Number 5, add electrons to balance charge. Now, these first 5 steps you do for both the oxidation and the reduction reactions. Nothing will be different between those for those steps. And so what we do here at the end, though, is after we split them up apart, we're going to recombine them back into the overall reaction. So 6. Multiply the half reactions in such a way that the electrons will cancel out. Then add the reactions together to rebuild the overall reaction. Multiply the half reactions in such a way that the electrons cancel. Then add the reactions together. To rebuild the overall reaction. Now, if you're doing this in an acidic condition, you are done. I'm going to put the last 3 steps that you would do in a base. If in a base, do 1 through 6, then we just have to convert it. So number 7 is add the same number of OH minus to both sides to cancel the H plus. Really, 7 and 8 could be combined. Combine H plus and OH minus to make waters. And then cancel H2Os when adding. And we'll do some examples, make no mistake. We'll do plenty. Okay. How many examples do I want to do? Oh man. Maybe I'll do these 3 or 4 pages and then we'll call it maybe. I don't want too many people to have to rely on this recording. Okay, are you guys with me so far? Just yes, Tristan. Oh, he's not even there. All right, Harvey and Young, just say yes.
Sorry, I pressed my space bar and it didn't do anything. Yes, we're with you.
Okay.
Yes.
Good. Whoa, who just yelled? Was that you, Chef? Oh no, that was Young. That was Miss Young. All right, so let's do some of these. And I'm gonna go ahead and start by just looking at half reactions. So let us look at half reactions to warm up. So what I mean is, I'm going to pretend that I've already taken some sort of overall reaction and I've already split it up into its half reactions. Let's just practice balancing half reactions before we move all the way to adding everything up. Okay. I'm going to do this by steps. So you'll see me writing a lot of things here. So I want to take a look at nitrate becoming nitrogen monoxide. That's this half reaction. Okay, so let's go with Soto. Do you actually have a mic or what, bud? Chat me if you don't have a mic. Speak if you do. I assume that means no mic. All right, Ben, I know you can talk. Let's do this. The first thing I have to do is to balance everything that is not oxygen or hydrogen.
So if we're not balancing oxygen, then the equation is balanced?
Yes. So far, so good. So, let's see. Balance the nitrogen. Check, right? Because that's the only thing we have to do. There's 1 and 1. So now we have to balance the oxygens, right? So I've got NO3 minus becoming NO. How many oxygens are on the left?
3,
On the right?
1.
So how do we get 2 more oxygens?
Add O2.
Add 2 H2Os. We're going to add waters to do that. So now we see that we have 2 oxygens, 3 oxygens. We are balanced on the oxygens. Next, we need to balance the hydrogens. So I have NO3 minus, goes to make NO, plus 2 H2Os. And of course, we're going to balance the hydrogens. How many hydrogens on the left?
0.
On the right?
4.
4. Oops. So I need to add 4 H pluses to balance them. And lastly, I'm going to need to balance charge. So I currently still have my 4 H pluses plus an NO3 minus, goes to make NO, plus 2 H2Os. Ben, what is the charge on the left?
Positive 3.
Positive 3. Does everyone, or does somebody not see the positive 3? Okay, so I'm assuming you all see that, right? We have 4 positives and 1 negative. What's the charge on the right, Ben?
0.
0. So how do I get a positive 3 to look like 0?
Add 3 electrons.
On that left-hand side. So now we have 0 equals 0. Guys, okay?
Yeah.
Chef?
Yeah, I'm good.
Okay. Harvey?
Good.
Cool. All right. Let's do another one. Oh, I guess I should have said example, huh? I should have said example. So I can do this one. I'm actually going to start doing this one in colors too. Let's say that I have, before I do that, what type of reaction is this? An oxidation or reduction? Tristan? Your mic's on.
Yeah, it's a oxidation.
It is a reduction.
Oh, shit.
Okay. This is a, actually, I can go and put that in a different color. This is a reduction reaction. Why? So this is where, when you're looking at the equation, there's actually going to be two ways that we can look at whether or not it's an oxidation or reduction. There's going to be two ways to know. Why? Two ways to know. First of all, right? It gained electrons. I don't like how I wrote that. First of all, it gained electrons. Right, it's on the reactant side. It is being given to it. It is consuming them. But this is the clever one. Second, look at nitrogen. Ooh. What is, oh, what's this word? Oh, formal charge. You guys remember this? Somebody say they remember formal charge?
Yes.
Chef was about to say yes too, right?
I feel like valence electrons plus something, or
Plus a blah blah on something like that. But let's take a look at this. That formal charge was the charge that thing is taking. So let's take a look at NO3. NO3 minus. Oxygen will become O2 minus. The most electronegative thing will become the charge that it wants. There are 3 oxygens. That means that's a -6 charge. Overall, it is -1 charge. Therefore, nitrogen is a, what's the difference between -6 and -1? Nitrogen's a +5. What about NO? Oxygen will become an O2 minus. There's 1 oxygen. That's a -2 charge. There is overall no charge. Therefore, nitrogen is a +2. Nitrogen's charge is reduced from +5 to +2. Bam, Christmas jammies. So there are 2 ways to look at this. You can either look at that reaction as we balanced it and say, oh, the electrons are on the reactant side, so it is gaining electrons, therefore a reduction. Or you can look at the players, the nitrate and the nitrogen monoxide, and say, well, what's that nitrogen doing? Because we know that oxygen is going to stay as a -2. And if you do that, you see that it goes from a 5 down to a 2, and its charge is reduced. So it's reduction. That's cool. At least I think it is. Preguntas?
Wait, so if it was an oxidation, nitrogen's charge would have
Would go up.
gained?
It would go up. If it's oxidation, it'll go up.
So nitrogen would have gone from like a 2 to a 5.
Yes. If this reaction were reversed, we'd be looking at the oxidation, and it would be going from the 2 to the 5. That is correct. All right. Example. I have permanganate, MnO4 minus, going to, what is that? Manganese 3 oxide. Gonna move that over just a touch. Okay, Harvey, before we even get started, is this an oxidation or a reduction?
Reduction. Wait, no, the other one.
Before we get going, is it oxidation or reduction? And you said it is?
Oxidation.
It is reduction. All right, in MnO4 minus, the manganese is what charge, Harvey?
Wait, I'm still writing it down.
Oh, okay. Well, I'm covering it up with my hand so you can't see it.
7 plus.
7 plus, how did you get that?
It's the difference between the charge of the oxygens and the overall charge.
That's right. Oxygen is a -2. There are 4 of them, which means oxygen is contributing a -8. Overall, it's a -1. So that means that manganese must have been, or is, a +7. So in the Mn2O3, we know that the oxygen is a 2. 2 times 3 is 6. There are 2 manganese. The manganese becomes a +3. The charge is reduced. So if we get a feel for that at the outset, it'll help us. It'll help us when we balance so that when we get to the end, if our electrons are on the wrong side, we know we did something wrong. Since we now know it's a reduction, we should see those on the reactant side gaining the electrons. I'm going to rewrite it down here for us. So I'm going to say MnO4 minus goes to make Mn2O3. I'm going to balance my manganese. And so let's see, Patrick, are you sticking around? You want to do this one with me?
Sure.
Oh, yeah, I mean, with that kind of enthusiasm, you don't have to. I'm just saying. All right, Patrick. All right, let's balance those manganese.
Okay, so for this one, we need to add 1 more manganese on the left.
Yeah, so to do that, we put a 2, right?
Yeah.
2 MnO4 minus goes to make Mn2O3. The next step is to balance the oxygens. I'm going to go ahead and do that in red.
Okay, so
How many
we have-
oxygens on the left?
We have 8 on the left and then 3 on the right.
So then we have to,
Add 5 H2Os on the right.
that is correct. So I'm still going to keep putting all of these steps here. Eventually I'll just use the colors and we will we'll be well versed enough to play the mental game here. Okay, so then what do we do?
Now I think we're going to do the hydrogens.
Yes, so how many hydrogens on the left?
0 and 10 on the right.
So then I put,
10 H pluses on the left.
okay. So I'm just now finishing this thing out, and I'm just going to keep track of where I'm going. Eventually, we're just going, I'll go ahead and still keep the colors, but we'll just, we'll do this all in one line because who wants to write this much, right? All right, now we're finally down to the electrons. So
now
let me just point out, this is atoms, this is oxygen, this is hydrogen, and now we're down to the electrons. So what's the charge on the left? Sorry about that.
I believe it's a positive 8.
It is a positive 8 because you have a positive 10 and a negative 2. What's the charge on the right-hand side?
0.
0. So then?
We add 8 electrons on the left.
That is correct. 8 electrons plus 10 hydrogens plus the 2 MnO4 minuses goes to make Mn2O3 plus 5 H2Os. All right, I want to see how far I get to go here. Let's see, it's almost 11. We could probably, how many lectures do we have left? We have 1, 2, 3, I think. I think that's plenty after this. So we'll just do a couple more examples because I'd really like to get more people involved in balancing these to make sure so they can ask questions. So we'll just do a couple more here, and then we will we'll call it a day. So let's do. Go ahead.
We only have 3 lectures after this.
Maybe. Does it seem right? So next week, Chem 110 has their exam, so that's Monday, Wednesday. Okay, so we have next week, Tuesday, Thursday. The week after that, Tuesday. I mean, we could have 4 lectures looking at it because I want to see if I can still get us one more day coming back after taking our 3rd exam so we can basically kind of have a day to review, if you will, or ask questions about things.
That'd be nice.
So we have 3 or 4 lectures. So we actually probably have plenty, especially because, I mean, let's face it, I've got no time constraints. If I have to go long on a lecture, I will. We can do this. I just don't want to make some of this too long right now because too many people are going to be watching this one such that they zone out and I can't keep their attention. So yeah, I want plenty of time. All right, let's do another one. And do you want me to still do all the steps written out like I've been doing, or do you just want me to write it on one line and go back and forth with colors?
I think one line.
Back and forth the colors will be fine.
One line in colors, Patrick, you said?
Yeah, that'd be fine.
Okay. Dwayne, you all right? No, you're not talking to me. Ben, I'm sure you're fine. It's Young and Harvey and Plunkett.
One line with colors.
Yeah, that's fine.
All right, there we go. You heard them, folks. If you can't follow along, it's their fault. All right. Triiodide going to iodate. Okay. First of all, just to be clear, is this going to be an oxidation or a reduction? Try iodine. What is the charge on the iodine? Whoa, did I just blow your mind? There's 3 of them, and it's a -1. So each of them is technically carrying a 1/3 charge. IO3 minus. Oxygen is a -2. There's 6 of them. Take 1 away. That iodine becomes a +5. The charge increase. It is oxidation. Charge did not reduce. Therefore, oxidation. Okay, that aside. First things first, are you guys okay with those charges and how I did them? Yes, good. All right, the first thing we need to balance is the iodines. So if we take a look at that, we have 3 on the left, we have 1 on the right. So we now need to bring us in and say, we need 3 of the iodates. Actually, Tristan, do you want to take this one?
Yeah, sure.
Was that yes, sure, or yes, sir?
Yes, sir.
Smell that, rabbit? Smells like beer. All right. How many oxygens on the left?
There are no oxygens on the left.
On the right?
There are now 9.
There are 9, so we need?
We are going to need 9 H2Os on the left.
Okay. Next, we balance the?
H hydrogen.
How many
So-
on the left?
18.
On the right?
None.
So then we have to?
Add 18 hydrogens to the right.
Okay. The last thing we need to do is balance the
Charge.
charge. All right, what is the charge on the left?
1 minus.
On the right?
Positive 15 looks like.
Positive 15. Does everyone see that? We have the 3 times the -1, and we have the 18 positives. That is a positive 15. Tristan, make positive 15 look like -1.
We're going to need to add 14 electrons to the right.
16
Wait,
electrons
no,
is
no.
correct.
Yeah. That's what
Now, what you just did, Tristan, is the classic mistake, and that's I'm glad you actually did that, because this is where you have to really kind of think about, okay, what's the charge on one side, what's the charge on the other, how do I make them look the same? This is probably the step that people need to keep the most cuidado. You got to be very careful on that part. Even I mess it up sometimes if I go too fast. So just be very cognizant of how you're adding and subtracting on those. All right. I'm going to give this next one to Miss Young. We have S2O3 with a 2 minus. Goes to make S4O6 with a 2 minus. So let's go ahead and balance that. I know you can talk because Harvey can talk.
Wait, I'm still figuring out the charges.
Oh, because you want to actually, well, you know what? We could do, well, okay, you can do that first. On this one, just because there's so much, I probably would have just jumped into balancing it and figured it out at the end, and then maybe confirmed with the charges. When it's a little harder, sometimes I go about it that way.
Wait, so you can figure out at the end if it's oxidation or reduction?
Yeah, you can always figure it out at the end. I've been doing it at the beginning because these calculations that we're seeing right here, these guys are easy. The one that you're doing right now is a little more complex. So if it's not immediately intuitive, I tend to just do it and then just double check at the end if I have to.
Okay. So it needs to be 2, 3,
So the first thing we do is we balance,
okay, so you'd put a 2 in front of the S2O3 2 minus on the left.
right? Because we're balancing the sulfurs. Then next we're going to balance.
The oxygen,
Okay, how many oxygens on the left?
6, and 6 on the right.
Okay, now what do we balance?
Hydrogen,
Okay,
there is no hydrogen.
okay, and then we balance.
Charge.
Okay,
So we need to add 2 electrons on the right, right?
Well, that was easy.
Yeah.
sometimes that easy, guys. Even though we have all these steps, if you don't need to do something, don't do it. Now, if you were to figure out those charges, Miss Young, what do we have here? On the S2O3, that sulfur is, we have 3 times -2 here for the oxygen. It's -6. There's already -2. So we're really looking at a -4. So we need a +4 to balance it. This sulfur is a +2. On the S406, or sorry, yeah, S406, there's 6 oxygens. That's a -12. There's already a 2 up there, so that's really -10. And now you got a 4, so 10 divided by 4 is 2.5. So the charge increased. Our charge did not reduce, since I keep using reduction for reduction. So it's just another way to double check yourself. You don't have to. If you're confident in your abilities at the beginning, you can see that it's not gaining electrons, so it is oxidized. It's also not gaining electrons, so it's oxidation. Losing, or you might say giving off electrons. Okay. Let's do, should I stop there? Let's go ahead and stop there, because what I'm going to do next is actually take some half reactions and decide to add them together to do the overall. So this is probably a good breaking point so that the rest of the people can catch up with us, and on Tuesday we can sally forth. Any questions about what's going on there? Seeing none, I guess I will stop recording.